Okay, so welcome back for the third week of this course. So in the last week where we ended, we were discussing about language modeling. We talked about the basics of language modeling. Then we talked about how do we evaluate a language model, and then we came to the topic of smoothing. Okay, so what was the simple idea we discussed? What is my add one smoothing, where I add 1 to each individual count, and accordingly I do some normalization in my denominator. And we ended by saying there are certain simple variants possible, like add k. I can also do unigram prior smoothing by, instead of adding a uniform weight to each word, I add a weight that is dependent on the probability of that word, unigram probability for that word. And that we were arguing that might work better than simply adding uniform count to each of the bigrams. There we had certain parameters like what will be a best way of choosing k and m in different models. Okay, so simple answer would be, so there is no unique value that you can choose. Suppose you have some held out data, so you can try to find out for which value of k and m you are getting the best perplexity for the held out data, and that can be one possible way of choosing the values of k and m. Okay, so now today we will go beyond the advanced smoothing and talk about some other advanced smoothing methods. Okay, so we'll start with two different smoothing methods called Good-turing smoothing and Kneser-Ney smoothing. So what is the intuition behind using a Good-turing smoothing? So intuition is essentially I want to find out what should be the probability for the words that I have not seen in my training data. So what Good-turing smoothing says, okay, so why don't you use the estimate of the things you have seen once in your training data to estimate about the things you have not seen. Similarly, whatever you have seen twice, use that to estimate the things you will see once, and like that. Okay, so this just tries to adjust the probability mass so that the things that were seen twice are used to find the probability for the things that were seen once. Things that were seen once are used to estimate the probability for the things that were not seen at all. Okay, so the idea is that we have to use the count of things we have seen once to find the count of things we have never seen. Okay, so for that let us first define what is the frequency of frequency. Okay, we used it in one of the earlier lectures also. So suppose I take these three sentences. Okay, I am here, who am I would like. From these sentences I am trying to construct the frequency of frequency. So that is how many words occur once, how many words occur twice, and so on. So if you see here, the word I occurs thrice, m occurs twice, and the other four words occur once. So what will be my frequency of frequency? I will find out how many of words occurs once with frequency 1. So that is my n1. So there are 4 words here that occur only once, so n1 is 4. Now I will see how many words occur twice, so how many words have a frequency of 2. So that I will have 1 here, and 3 is 1. So this is my frequency of frequency. Okay, so 4 words occur once, 1 word occurs twice, 1 word occurs thrice. Now how do I use that in Good-turing estimate? So what is the idea? So this we discussed earlier. So I want to reallocate the probability mass of n-grams that occur r+1 times in the training data to the n-grams that occur r times. Okay, specifically you want to see the n-grams that occur once to find the probability mass for the n-grams that occur 0 times. But you do that in general. Okay, so the n-grams that occur r+1 times, use that for r times. Okay, so now in particular reallocate the probability mass for n-grams that were seen once for those that were never seen. So now we should see formally what will be the effective probability mass n count that we will get by this Good-turing estimate. Okay, so let us see. Suppose I want to find out for words that occurred c times. Words that occur c times, what will be the effective adjusted count after applying Good-turing estimate? Okay, so now how we define that? So what would happen in my training data? I'll have words that occur 0 times, words that occur 1 time, let it be n0, n1, words that occur twice, n2, and so on. So the n2 number of words that occur twice. Similarly, now there are nc number of words that occur c times, nc plus 1 words that occur c plus 1 times. Okay. Now I want to use Good-Turing to estimate the count for these words that occur c times. So what did we say? We said we will use this probability mass and give it to these words. Now how do we distribute? So what is the probability mass associated with the words that occur c plus 1 times? Okay. So now suppose there are n words or n bigrams in total. Okay. So now what is the probability mass for the bigrams that occurred, or n-gram you can say in general, that occurred c plus 1 times? You see how many n-grams are there? There are nc plus 1 different n-grams. So what will be the probability mass for them? It will be nc plus 1 times c plus 1 divided by the total number of n-grams, that are n, that is the probability mass. Yes, and this I am distributing to the words that occur c times. Now how many words are there? There are nc words. So what is the probability that each of them will get? Divide by nc. Yes. So now, so this is the probability mass for that each of them will get. Now what will be their effective count? Remember how we defined effective count? C star, such that if I divide it by n mle, this will give me the same probability. So that will tell me C star is nc plus 1 times c plus 1 divided by nc, and that's what we have written here. Okay. So nc in general is the n-grams that are seen exactly c times in the corpus. So by using this definition, I can find out what is the effective count for any word that has occurred any c number of times in the corpus. Okay. So that's what we have seen. So this is the probability for the words, things that are seen c times c star by n. Yes, c star is my nothing but my effective n-gram count. Okay. Now what about the words that were not seen at all? That are the words that are whenever I am saying words here, it means the n-grams in general. So what about the n-grams that did not occur at all in my training data? So from my definition, I'll use the probability mass of the words that were seen once. Okay. So what is the probability mass? So there are, by definition, there are n1 words that were seen once. So each of them occurs once. So what is the probability mass? It is n1 by n. Yes, and this probability mass I'll give to the words that were seen 0 times. Yes. Now you might have a question, how much of this each of them individually will get? So this is the probability mass that the n-grams that did not occur in the corpus together will get. But how much of this individually each of them will get? So we can just divide it by the number of n-grams that did not occur in the corpus. So we will see in some simple example how can we estimate this value. Okay. So here, if my count is 0, so Good-Turing estimate for the things that were frequency c, when c is 0 is n1 by n, that we just saw. Okay, so that is the effective probability mass that I will give to all the words or n-grams that did not occur in the training data. Okay, so this gives me a nice method of estimating the probability for the words that did not occur in my training data. Now there are certain complications that you might have when you are applying this Good-Turing estimate. So for small c, generally you will see that nc is greater than nc plus 1. That is the number of words having a frequency c is greater than number of words having a frequency c plus 1. So remember what is particular empirical law that states that? So that is the Gibbs law that states that there is an inverse relationship. So this will generally hold. But it might happen when you go to very high frequencies. Certain frequencies are not observing that. So this is possible. Okay. So what do we do in general? So when we go to higher and higher frequencies for larger case or larger siege here, we can replace it with some sort of best fit power law, and we will do some normalization. Okay. So instead of doing it for each individual k, I might actually just fit. So I have n1, n2, and so on. And when I go to the higher values, I simply fit some sort of power law, and that is so that it is normalized, and I'll obtain the same probability mass, that is 1. Okay. So this power law can be fitted in general. So in various toolkits that where you might use these methods, they do it for only few values of k, it's initial few values of k, maybe k is equal to 5 or k is equal to 10. Okay. And then the formula that we were using might have to be readjusted. Okay. But the basic idea is same what we have seen here. Okay. So now suppose we apply this Good-turing smoothing method for a corpus like AP news wire, okay, academic press news. There are 22 million words, and so that's where you are seeing for different counts what is the Good-turing estimate that was seen. This is for bigrams. Okay. So what you are observing in the table, so for the bigrams that occurred 0 number of times, the Good-turing estimate was 0.000270. Okay. For once 0.446, for twice 0.126. Now, so how do I actually get this number 0.0000270? So we can just do that quickly. So remember, for the words that occur 0 times, what is the total probability that we are giving them? We are giving them the probability of n1 divided by n. Okay. Now what is the probability given to the individual word? So you multiply by n0. N0 is the number of bigrams that occurring 0 times. Okay. What will be the effective count? Effective count, you will remove this n. Yes. So it will be n1 divided by n0. Now what is n1? So you need to find out how many bigrams occurred once. Yes, that you can find from the data. How do you find n0? That is how many bigrams did not occur in my data. Now, if you remember from Shakespeare's corpus, so how do we find out how many bigrams did not occur at all? So we need to see what is my vocabulary size, what are different unigrams. Okay. Suppose I have my vocabulary size of V. That is my number of unigrams. So how many bigrams are possible? V square bigrams are possible. So how many actually occurred? Suppose I know that out of these some NB bigrams occurred in my corpus. So V square minus NB gives me the bigrams that did not occur at all in my corpus. So this will become my N0, number of bigrams that did not occur in my corpus. So this value I obtain by finding out N1, number of bigrams that occur once, divided by V square minus NB. NB is the number of bigrams in total. So that is the unique bigrams that occur in my corpus. Okay. Now, what is the other observation that you might have from this table by looking at this table? So for 0 and 1 this is different, but once you start seeing from 2 onwards, what is the pattern that you see? You see that most of the effective counts are the original count minus some value like 0.75. Okay. So you see all of these are roughly original value minus 0.7275. So now one might argue, why don't I just use C minus 0.75, okay, and maybe give a different value to the initial two counts. So that is also done in practice, okay, and this is called the absolute discounting. That's what we will see next. So the idea is that why don't I subtract something like 0.75 or some d from each bigram that occur more than, say, more than once or whatever, okay, and I can have one or two different values of d for some initial bigrams, and this is called the absolute discounting method. And you can probably interpolate it with my unigram probability that we saw in the last lecture to give a better estimate. Yes, this is called linear interpolation with the unigram probability of the absolute discounting method, and that is the formula that we have written here. So this is, I am doing some sort of discounting from each bigram count, yes, plus I am interpolating it with my unigram probability with some weight lambda wi minus 1. Why do I need a weight here? So that when I sum up this probability absolute discounting, wi given wi minus 1, for each individual wi, this will add up to 1. So that's why I need some sort of normalization constant that will make sure that this will add up to 1. Okay, so we can keep probably some values of d for counts 1 and 2, and otherwise I can use this particular interpolation method. Now, that's where the idea of our other advanced smoothing model comes. That was our Kneser-Ney smoothing method. So what is that? Okay, so that is, can we do better than using the regular unigram correct? Okay, so see, so when we first started with a simple add-1 smoothing, we were giving uniform weight to each part to the n-gram, uniform addition. Then from there we moved on to unigram prior. We said, okay, why do we give uniformly? We give a higher weight to the words that occur more often in my corpus. Now we are saying, can we do better than even this? And that's where we will see the Kneser-Ney smoothing idea. So what is the idea? So now again, let us go to the Shannon's game. Okay, suppose I have the sentence, I can't see without my reading, and I have to fill in this blank. And suppose possibilities are glasses and Francisco, and all of us will say, okay, I should fill in glasses here. Now take a scenario where reading glasses does not occur in my training data, and reading Francisco also does not occur in my training data. Now if I use the previous model, what will I do? The probability of filling in glasses versus Francisco will depend on their unigram probabilities. And suppose this is my data from some US corpus, so I will find probability of Francisco is higher than probability of glasses. Okay, that can very well happen, and that means I will end up filling it Francisco here. That is not the correct choice here. Okay, so can we do something better than simply using their unigram probabilities? That is the idea of Kneser-Ney smoothing. So Francisco is more common than glasses in my data, but can I use this idea that in my data, whenever I see Francisco, it occurs only after San, in this occurrence San Francisco. On the other hand, whenever I see glasses, it occurs after multiple different words. Okay, so this is the intuition. That is, I'll see, given a word, what are the other words it comes with. Okay, so here if I take word as Francisco, it occurs maybe with only one word. Yes, only one word, San. But glasses occurs with many other words, right? It can occur with different words, and this, so suppose glasses occurs with 10 different words, and Francisco occurs with only one different word. So what is the intuition? If a word occurs with many other words, that means it is more likely to complete this particular bigram that we are seeing right now. So after reading, a word is more likely to occur if it has already completed many other bigrams, if it is more commonly used as bigrams with many other words. This will not happen with Francisco, because Francisco is used only after San. So given a new context, probably Francisco is not a good choice. But glasses occurs with many other different words. So after a completely new context, glasses is a better choice than Francisco. So formally, how this method uses this intuition. So instead of using simple probability of this word, unigram probability, we use probability continuation word. So that is how likely is this word to appear as a novel continuation. What do I mean by novel continuation? How likely it is to complete a bigram or an n-gram. So how do I find out this probability? So for each word, to find this probability, as we said, we have to count the number of bigram types it completes. So how many bigrams where it occurs as the last word, the final word. Okay. Now for each bigram, whenever it occurred the first time, it was like a novel continuation. So that's what we mean by novel continuation probability here, that how many bigrams it is completing. So this will be simply, it will be proportional to the number of bigrams it is completing. So here how many wi minus 1 are there such that w occurs after that in my corpus. So that is the probability of continuation. Okay, it is the same thing. What is the probability of continuation? This should depend on the number of bigrams types it completes. Now, how should I normalize it? I want to find this probability for each word in the corpus. Yes, so this is proportional to the number of bigram types it completes. So I should find out in total how many bigram types are there that each word is completing. So that is effectively the number of bigram types in total, not tokens, the number of bigram types, how many different bigram types are there. Okay, so here also we are only taking the types, how many different bigram types we are completing. So I will normalize it by using all possible bigrams. So here this is all possible bigrams, because I am saying the count is greater than 0. In my training data, how many bigram types I have seen. So this will give me the probability continuation of the word W. Okay. So once I have found this probability, I can even go back to my unigram prior based absolute discounting method and replace PWI by P continuation WI. Okay. And that is my Kneser-Ney smoothing model. So instead of using the unigram prior for smoothing, I use this Kneser-Ney smoothing by using the continuation probability. Okay. So if I do that, a frequent word like Francisco occurring only in one context of Sam will have a lower continuation probability. So this will be my model with Kneser-Ney smoothing. You see, so all these are, this is all same, this is same. Now instead of PWI, we have put P continuation WI that we get from the previous slide, whatever formula we wrote in the previous slide, that will give me this P continuation WI. Okay. Now, so there is one question here that we discussed even in the earlier example. How do we find lambda Wi minus 1? So what was the intuition I gave? The hint was that lambda Wi minus 1 should be such that summation over Kn smoothing of Wi given Wi minus 1 for all Wi in my vocabulary should be 1. So now you can take it as a simple exercise that suppose I want to find out what will be the value of lambda Wi minus 1 for this particular formula. Okay, and you can assume that D lies between 0 to 1. Okay, for this particular case, what is the value of lambda Wi minus 1 that I will get? Okay, so the answer is also on this slide. So you will get a lambda Wi minus 1 of this. So try to find out, if I have to satisfy the constraint that the summation of probabilities for all the words should add up to 1, what is the value of lambda that I end up with? Okay, and that will give you this particular value. Okay. Now, so other than these two models of Good-turing and Kneser-Ney smoothing, there are other smoothing models that you might be able to use. Okay. So one simple idea, instead of using a new smoothing model, why don't we combine various models? So remember, we were already doing that somewhere. So for computing bigram, I was trying to use the probability of the unigram for unigram prior smoothing. Now can I generalize this idea? Suppose I am finding out the trigram probability, trigram language model. Now from my data I can compute the trigram language model probabilities, bigram and unigram using the MLE. Can I try to effectively combine these different probability models to find my trigram language model? Okay. So there are actually two very popular ways in which this can be done. One is called interpolation based methods, another is called Backoff language models. So we will just see some simple intuitions on how this can be combined together. So what we have seen, as I increase my n, power of my n-gram model increases. We also saw that when I saw the perplexity values. When I take a larger n-gram, I get lower perplexity, I get better perplexity, that means. So that means the model becomes much better when I take a larger n. But what is the problem that happens if I take a larger n? Remember why we did all this smoothing? Because when I am taking larger n, the data becomes more and more sparse. So many of the actual n-grams become 0, their probability becomes 0. So at one side, higher n-gram are better, a trigram model is better, other side it is very sparse. So why can't I take advantage of the both things? That is, I take a higher order n-gram model whenever I have the data, but whenever I do not have the data, I try to use the low n-gram model. So I do that together in a single model. So that is the basic idea of these models that we will see. So now general approach is, can we combine multiple n-gram models to get a single model that can also take the advantage of large n-gram model but avoid the sparseness problem. Okay. So that is, some cases it might help to use less context whenever you do not have information about larger data, larger context. So in Backoff, what you will do, suppose I am computing a trigram language model. So wi given wi minus 1, wi minus 2, whenever this trigram occurs in my training data, I will use the probability as per my MLE. But if it does not occur in my training data, I will back off to my bigram language model. So that means whenever the count of wi minus 1, wi is greater than 0, I will go to bigram. Suppose that it is also 0, then I will go to unigram. So this is the idea of Backoff language model. So if you have good evidence, you go to trigram, otherwise you go to bigram, otherwise you go to unigram. Okay. On the other hand, interpolation, you compute all three and just interpolate them together. You try to mix these together. Okay. So let us see what do we do in Backoff language models. So idea is that I am computing a trigram model, wi given wi minus 2 I minus 1, and so here this is the previous word and this is previous to previous word. Okay. So if I do not have counts for wi minus 2, wi minus 1, wi, suppose this is 0, then I use probably wi given wi minus 1. Now suppose count of wi minus 1, wi is also 0, then you go to probability wi. Okay. Now, so but you might end up having some problems with how do I normalize the final probability distribution that I will get. Okay. So this is the particular formula, recursive formula of Backoff that you can use. So Backoff for this trigram model, wi given wi minus 2 wi minus 1 is p hat wi given wi minus 2 wi minus 1 if the count is greater than 0. Now what is p hat? This is actually similar to my maximum likelihood estimate that you will get, but it has been, something has been subtracted from there. So some probability mass has been stolen from there, so that it can be given to the other counts. Why we need that? Suppose you are computing this trigram Backoff probability model. So in general, you are doing it after Wi minus 2, Wi minus 1. You are finding for various words W1, W2, W3. Okay. Suppose this occurs 3 times, this occurs 2 times, this occurs 0 times. So now once you use the MLE estimate, immediately this will have a probability of 3 by 5. This will have a probability of 2 by 5. Suppose there is no other bigram, and this will have a probability of 0. And now you want to use Backoff to go to find huge probability W3 given Wi minus 1. But here itself the probability mass is adding up to 1. So how can you use the bigram probability? So for that you might have to reduce some mass from these two values. So that's why we are writing p hat. And there are different ways you can reduce. So we will take one simple example where you are doing it by some simple constant. You are reducing some simple constant. But this can be proportional also. You can multiply some factor less than 1. Okay. So you will take, that is my p hat. It's a reduced probability value from my MLE estimate. Okay. So now if the count is greater than 0, I take p hat. If the count is equal to 0, then I have to use the previous, I have to back off to the bigram model. So I have to use probability Wi given Wi minus 1, and that's where I back off to this model. But what is interesting that you are seeing here, so this is a recursive definition. I am using the Backoff probability of Wi given Wi minus 1, and I am multiplying with some constant again to ensure that the probability mass adds up to 1. Okay. So now, so recursive definition. So how do we define probability Wi given Wi minus 1? Again, it's p hat Wi given Wi minus 1 if the count is greater than 0, and p hat Wn if the count is equal to 0. Okay. So I think it will help if we take a simple example and try to see how do we actually use this definition to compute the Backoff probabilities. Okay. So let's take an example. Okay. So here we are taking a corpus where we are having only 4 words A, B, C and D, and this is some data that is provided. So what is this data? So this is, it is telling how many times A occurs after AB. It occurs 4 times. On the other hand, B occurs after AB 0 times, C occurs after AB 0 times. Okay. Similarly, A occurs after B 5 times, B occurs after B 3 times, C occurs after B 0 times, and also the individual words, A occurs 8 times, B occurs 9 times, C occurs 8 times, D occurs 7 times. Now given this data, you are asked to compute the Backoff probability model of Wn given Wn minus 2 n minus 1, where the previous word is B and previous to previous word is A. Okay. And you also told that you can use this simple definition for p hat, that is px minus 1 by 8. So suppose I want to use that to find out the Backoff probability distribution. Now, so that is nothing but probability Backoff of word given A and B. A is previous to previous word and B is the previous word. Okay. So let us try to do that. So I want to find out the Backoff probability W given AB. So this would be W can take A, B, C and D. So right now from my table, what are the counts I am seeing? A occurs, so this occurs 4 times, this occurs 0 times, this occurs 0 times, this occurs 0 times. Okay. So as from my definition of Backoff probability, I can say that this probability will be p hat A given AB, because the count is greater than 0, but this will be lambda times previous two words AB, so this lambda AB, a constant, times Backoff probability of, so I will go to the previous word, Backoff probability of B given B. This will be lambda AB times Backoff probability of C given the previous word B, and this will be lambda AB Backoff probability of D given B. So what it says is that now you have to compute the Backoff probability of B given B, C given B, and D given B. Okay. So again you can use the definition. So now I am computing Backoff probability of W given B, and W is equal to A, B, C, and D. Now I see A occurs 5 times, B occurs 3 times, C occurs 0 times, D occurs 0 times. So now as per my definition, this will be P hat A given B. What will be that? That will be 5 by 8, yes, minus 1 by 8, that is 4 by 8. What will be this? P hat B given B, 3 by 8 minus 1 by 8, that is 2 by 8. Now what will be this? This occurs 0 number of times, so this will be lambda of B times unigram probability of C, maybe P hat C. Okay. Now what is this? We can see from my data what is P hat C. So C occurs 8 times, yes, and total number of, so what is the total of my unigram count? If you add, it will add up to 32. Okay. So this, so PC, the MLE value is, so it's lambda B times PC minus 1 by 8. PC is 8 by 32, yes. So this will become 8 by 32, 1 by 4 minus 1 by 8. So that will be lambda B times 1 by 8. Okay. Similarly, for D is equal to 0, I can write lambda B times P hat D, that is lambda B times PD minus 1 by 8. Okay. That is lambda B times PD here was 7 by 32, 7 by 32 minus 1 by 8. Okay. So that will be lambda B times, this will be 7 minus 4, 3 by 32. Okay. So suppose you get these values. Now how will you compute the how will you go to the probability B or W given AB? You have to first find what is the Backoff probabilities of for these two cases C and D. So for that you have to find what is the value of lambda B. Now how do you find lambda B? You have to normalize this, right? So you will say lambda B times 1 by 8 plus 3 by 32 plus 4 by 8 plus 2 by 8 should give me 1, right? This should be 1 for if you sum over all the words. So what does this say? Lambda B times 7 by 32 is equal to 1 minus 6 by 8, so that is 2 by 8. So what is lambda B? So you will get, okay, so you get as 8 by 7. So once if you substitute lambda B as 8 by 7 here, that will give you this probability as, so you will find this probability and this probability also. So you have the Backoff probability for this. Now put this Backoff probability here and you have a constant. How do you find this constant? Again you will have to normalize it. Lambda AB times summation of this plus this probability should add up to 1, that will give you my lambda AB and also give you this probability distribution. So that's how you find the Backoff probability distribution using this recursive definition. Okay. And what do we do in interpolation? We have different unigram, bigram, trigram models. I try to interpolate them in different proportions. Okay. So what we are doing here, we have computed a trigram model, bigram model, unigram model, and different proportions lambda 1, lambda 2, lambda 3 are given to those. Okay, such that they will add up to 1. In general, you can also condition your lambdas on the context. Okay, what is your previous and previous to previous word? The lambda might depend on that. So this is the same equation, except that now lambdas are depending on the context. Okay, and now the question might be, how do I choose a held out corpus? How do I choose my lambdas? So that you will do, as we said earlier, you will have an held out corpus. You will find out which values of lambda gives you the highest probability, and that lambdas you can use for your smoothing. Okay, so that's where we finish our topic of language modeling. So we covered a lot of simple smoothing methods and some advanced smoothing methods, and then we will now go to the next topic of. So we will start with the topic of morphology. Okay, so that will be the topic of the next lecture.